Kathy Page, our own co-chair, and Steve Yeager is the other co-chair. And I want to make sure that our online people do hear acknowledgement to the great work that Yaga has done as a co-chair of this group until she recently moved off in her new position. And also Sasha Glanville, who is the liaison for the Earth System Prediction Working Group. I'll highlight just the diversity, equity, and inclusion emphasis here, which I really appreciate this at NCAR. It's really important, and I'll just remind everyone, both online and in the room, to have a respectful dialogue. This is a working group. Let's be positive and forward thinking, and offer that constructive feedback. Consider new ideas. Let's see if I can make this work properly. Here we go. Show appreciation, encourage innovation, acknowledge teamwork. None of us do anything in isolation, so I think that's a really important one. And share the air. So let's make sure we give everyone, especially in a workshop, a chance to speak, both online and in person. All right, a few reminders. This is an hybrid online and in-person meeting, so let's do our best to participate in an inclusive manner. We'll be patient with making sure we let the online people have a chance to speak up. It's always difficult when people are in the room and people are online, and so let's make sure that our dialogue in the room also, that the people online can be part of that. Second thing, this meeting is being recorded and live streamed. So if you have an upcoming talk today and you do not want your presentation recorded, you need to notify us immediately, because if you do not, it is impossible for us to change the way things are set up and your talk not be recorded. The other thing is that live streaming is done on your YouTube channel, which is subject to copyright laws. So please make sure that you're not violating any copyright laws in your presentation. So if you need to make a quick change to something you didn't give credit you should have or something like that, please do make those changes very quickly and re-upload. So I think there was one more thing. Oh yes, if you have not uploaded your presentation, that's mostly to the people online, because I think everyone in the room has uploaded. If you have not sent your presentation in, it's best if you go ahead and do that right away. That will guarantee that if there is a problem with you sharing your screen, some sort of technical detail that makes it difficult, we can easily share for you here and keep things moving smoothly. I think that was it. Yes, just the agenda. So we have a number of talks this morning before a 10:40 break, followed by the
It looks like we cannot hear you.
You cannot hear me. Is there something I need to do to address that? We're good. Okay, I've got a thumbs up from the back, so hopefully you can hear me now. Our agenda, we have a number of talks here before a 10:40 break. Then we have the CGD seminar at 11, and we will keep our schedule very tight so that we do not mess up the CGD seminar time. After seminar is lunch, and then we have a series of talks in the afternoon, ending with the discussion until about 4 o'clock. All right, so that is the intro. I think we're still all good with all right. We're all good with the help with the computing and Zoom or whatever, our online. So I'm going to go to the next talk. And is the next talk, is that speaker here? We're waiting for that speaker to arrive. Also,
there he is.
Neil is here, excellent, okay. And I don't know how to get to talks again. Screen.
Is he gonna share his talk, or are we sharing it?
I think he has to share it because I don't think we have it. So Eniola, you will need to share your screen. Share your talk on your screen.
Yeah, he's muted.
And you're muted.
Is it okay now?
Yes, we can hear you. All right.
I'm very sorry. I don't even have it at the back of my mind that I will be presenting, because I'm attending currently a conference a workshop Icarus, but I can still do the presentation.
All right, so are you able to share your screen?
So just give me a moment. I have to. This is my Linux system. What I want to share is in my window. I don't know if
Well,
I
why don't
can be
you
given a 5 minutes
try to
to go
share your
to
screen?
window and present it in about 5 minutes.
Okay, well, why don't we'll move you to the next, we're gonna go on to the next talk and give you
Yes.
time to take care of that. And so
Yeah.
we're gonna, we'll go to the next talk, which is going to be yoga.
Excuse me,
Yep.
could he send us his talk just so that we have?
Okay. Yes, I can send you.
Okay,
I can.
cool. All right, thank you. All right.
I will send it to. I don't know if it's going to. Oh no, it won't. But I will send you. Just go to the next talk. I will send you.
Okay, so we will move on to the next talk, which is yoga. So Yaga Richter will be talking about quantifying sources of subseasonal prediction skill in CESM 2. Where's my talk? I think they bring it up. Steve, do you know how to bring up the talk?
Yeah, bring it up.
Oh, now I see it's coming up. You should be sources. Is that you? Oh, excellent.
Good morning. This morning I'm going to talk about a project that took several years to complete, but we're finally there, and the paper was published just yesterday, which is really good timing with this meeting. And I'd like to acknowledge a lot of people's work that went into this, specifically Sasha, Tegan, Sanjeev, Steve, Nick, lots of other people, and we pulled in Meg Fowler in the very last stages of the manuscript as we got into really understanding the land-atmosphere interactions that are kind of becoming crucial to this project. All right, so we set out with a very basic goal is to quantify how much subseasonal predictability comes from the initial state of the atmosphere, land, and ocean initial conditions. And largely, we were really wanting to verify this figure on the left, which is Sasha recreated this based on a figure that Paul Diermeyer made back in the age, and this is shown all over the place as really that our best understanding of where predictability comes from the subseasonal timescale. And what you see is in the early stages, the predictability is supposed to be coming from the atmosphere, but the land contribution is supposed to be peaking at week 1 and 2, and then tailoring off. And according to this diagram, the contribution from the ocean comes in weeks past week 3, and especially as we get into weeks 5, 6. So we carried out a unique suite of experiments to see what this diagram looks like for CSM. And before I move on to those sources, also we discovered during the project, so the diagram talked about the atmosphere, land, and the ocean, but one of the things that we discovered you can't ignore that these are not independent, right? So these, specifically the land and the atmosphere are tightly coupled. There is a diagram on the right that describes all the complex interactions, and a lot of those interactions are through soil moisture and the transfer of heat fluxes between those lower layers of the atmosphere and the top of the land model, and those interactions happen on a very short time scales. And the atmosphere and ocean also interact, however, I think that interaction is a little slower. So ocean has a long heat capacity, so there is also interaction, surface fluxes, but that's a little bit different than over land. All right, so for our methods, we're going to focus on 2-meter temperature and also precipitation for weeks 1, 2, weeks 3, 4, and weeks 5, 6. Our primary measure of scale is the anomaly correlation coefficients, and that's anomalies based on lead-dependent climatology. And for observations, in most of the plots I'm going to show is ERA 5 2-meter temperature. And the reason for that is we also want to look over ocean, not over land. But Sasha has done all the plots also with CPC over land, and all the results don't change. There's just slight differences in magnitude. And then for precipitation, we're using GPCP. And the standard reforecast set is basically we initialize atmosphere, land, and ocean. So atmosphere is initialized from CFSV2. Land is spun off offline with also CFSV2 till it equilibrates. And then ocean utilizes the forest ocean simulations that Steve's been pioneering for years. So we kind of take a bunch of different initial conditions, put them into the model, and run our standard reforecast set with weekly initializations and 11-member ensemble. And because we have this, some people call hodgepodge or ad hoc initialization of the model, and we don't use data simulation that is fully consistent, we are able then take those initial conditions apart and change them out. So we've done 7 additional experimental suites that we replaced the realistic initialization with climatology. So for example, in our Clima ATM runs, the ocean and land are going to be initialized realistically, but the atmosphere starts with climatology and so forth. So Clima land is climatological land, and Clima ocean is climatological ocean. And then we also discovered that there wasn't quite enough. We weren't quite getting all the information that we needed, so we ran a suite, Clima All, where we removed any realistic initialization, and we expected the scale would be largely 0, and it largely is. I'll show that. But the reason we did that is then we one by one added the realistic initialization. So when we have climatological atmosphere and land, the only component that's realistically initialized is the ocean and so forth. So really lets us zone in is what skill we gain from adding in the realistic initialization, and the experience of the on the left give us what skill do we lose by not initializing from that component. All right, so I'm going to start with, this is the basic reforecast showing skill for 2-meter temperature. And all the plots are going to go the same. At weeks 1, 2 is on the top, 3, 4 moving to the middle, and weeks 5, 6 on the bottom. And not surprisingly, what you see over land areas as you go further into the forecast period, that you lose skill over land, but you don't lose skill over the ocean because the ocean holds memory a lot longer. And it becomes relevant later. But this is very comparable to what you find in other subseasonal models. So it's the skill of CSM2 is really not any different than on average from all the other models in sub-X. It is lower than ECMWF. However, it's comparable to most other models out there. And here on the right is the Clima All suite, so nothing is initialized realistically. And as you would expect, there is mostly no skill. There's slight significant areas in weeks 5, 6. There may be some contribution to changes in external forcing, but those are very small. For most practical purposes, there's no skill. So when you add one component initialized, you can treat that as the skill coming from that. All right, so we're going to break this down by atmospheric, starting from the atmosphere. So on the left is our standard reforecast suite, and in the middle is we took out the realistic atmospheric initialization, and we have climatological atmospheric conditions. And on the right, we only initialize the atmosphere and not the land and the ocean. So what you see is over land areas, immediately in weeks 1, 2, you lose a lot of skill. That's a very big difference from the standard reforecast. And this continues all the way through the reforecast period. And similarly, what you can see, if you just initialize the atmosphere, in weeks 1, 2, you can get back the standard skill almost immediately. So all the areas that are dotted here there's no statistical significant difference from skill from the original forecast. So this is already telling us that in weeks 1, 2, really the atmosphere is the key source of predictability for most of the land areas, and a little bit also in weeks 3, 4. So all of these stippled regions, when you only initialize the atmosphere, you're already getting back most of the skill that you had in a fully coupled system. All right, so that is really expected. This is really consistent with Paul's diagram. Now, where we got into things getting less expected is when we started looking at the role of land. So same format of the plots. And when you change land to climatology in weeks 1, 2, you see this almost the entire map is stippled. So we did not lose any skill. And as a matter of fact, if you look at South America and parts of Africa, we gained skill. This is not what we were really expecting. And the same thing, as you go down to weeks 3, 4, we are gaining skill from initializing with climatological land over parts of South America and also Africa. And similarly as we go to weeks 5, 6. So this is really something we didn't expect, because if the realistic land initialization had a crucial role, this skill should have dropped off. And if we just initialize with land, on the other hand, we get very little skill back, but especially in weeks 1, 2, we do get a substantial amount of skill back just from initializing the land. So why is this? So Sanjeev Kumar made this figure for us, starting to look, and we probably verified at least 10 different ways that we actually initialized the model properly, and one set of simulations was really climatological and the other wasn't. So this is one of those plots, and the land, we think that the key component there is the soil moisture. So this is Sanjeev's plot of looking at, in standard reforecast and CLIMA land, how is the soil moisture performing? So what we see is what we expect, that when you initialize soil moisture, then the prediction of soil moisture is going to be much better than we initialize with climatology. And this also shows that we did do the experiments correctly. There is almost no skill in soil moisture at the beginning of the forecasts when we initialize with climatology, as expected. And then here is another figure just looking at this point in the central United States. In a standard reforecast, we start off with pretty high skill at time 0, and then there is a decrease in skill of soil moisture, but this is still much higher skill than in climatology. However, that is not the situation, and I don't have the line plot here, but if you look closely at South America, the picture is actually opposite. That with climatological land, the forecast of soil moisture is also better going into those into the future, better than if we initialized it, right? So you see there's a big change from the beginning when there was no skill, when we faultily initialized it, but the climatological initialization, for whatever reason, the soil moisture is also doing better. So we dug in a little bit more into this, just to give you a little perspective. So what we expect from land atmosphere coupling is when you have high soil moisture, this leads to increased evaporative cooling and negative temperature anomalies. And also the opposite is true. When you have a soil drought, you should be getting positive temperature anomalies and then the feedbacks on the surface temperatures. And some of these other works have shown that the highest interaction is when you have both strong soil moisture evaporation coupling and long soil moisture memory. And according to Go et al. 2011, that's high soil moisture predictability in North America throughout spring and summer. However, low atmospheric predictability due to low atmosphere coupling strength. So this coupling strength seems to be the crucial part of the picture. So Mick Fowler made us this plot investigating what that coupling is in CSM1 and also in CSM2. And partly because Paul Diermeier's figure was based on some of the prior work. There was a GLACE2 project, et cetera. There was a multi-model comparison where they were looking at models, but that work was done with CSM1. So more or less what I'm going to show you here in these figures is that the coupling between the land atmosphere is weaker in CSM2 than it was in CSM1. So these plots of the left are for JJA, plots on the right are for DJF. And the quantity shown is this terrestrial coupling index. And what you see is in CSM2 that there is strong and negative coupling in the summer hemisphere. So there would be in the northern hemisphere here, and it would be southern hemisphere in DJF. And it's in the southern hemisphere, this is similar to CSM1 and to the observations, but in northern hemisphere, the coupling is weaker in CSM2 than in CSM1. And so this is our going hypothesis, is that the weaker impact of soil moisture on surface fluxes in the northern hemisphere is really the cause why we're not getting a strong connection. And there may be other reasons, but this definitely seems one striking difference and something we need to go into, investigate a little further. All right, so moving on onto the role of the ocean. So similar format of the plots, and in weeks 1, 2, we also don't see a whole lot of degradation of skill if we don't initialize the ocean. And this changes though as we get into weeks 5, 6. So over land in the northern hemisphere, there is not a whole lot of loss of skill, but where you see the loss of skill is largely in the tropics. And I'll show a line plot later where we separate the tropics from the northern hemisphere. But basically what you're seeing here, that's the ocean really provides a lot of skill in the ocean regions. And you do gain skill a lot in northern part of South America and in parts of Central America, but in the northern hemisphere, for whatever reason, we're also not harnessing a lot of skill from the ocean either. However, our free forecast period is only from 1999 to 2020, and we think the largest gain of skill would be from ENSO events. So we went ahead and picked those out, and this does show that there is an increased skill in weeks 3, 4, and weeks 5, 6, but primarily in the tropics, right? A little bit, you see a little bit in the Pacific Northwest, and this influence gets stronger as you go down into the forecast, into later in the forecast, weeks 5, 6 versus weeks 3, 4. So we anticipate, but we don't have the data as you keep going into the seasonal time scale, that the role of the ocean will be much more important. But I think in weeks 5, 6, you're still seeing the ENSO influence in the tropical regions related to where you see the ENSO. So imagine if you have stronger ENSO events, also that influence might be larger. All right, so some summary figures, going back to Paul's diagram. So this is the ACC of annual mean 2-meter temperature, and the black line is the standard reforecast, and the yellow is atmosphere, blue is ocean, and we added these dotted lines, which are our derivation of the land-atmosphere coupling terms, and for the ocean, it's the blue dotted lines. And what we also try to do is how linear are those responses. So when you add up all the curves here from all our specialized experiments, is what you see in the pink line. So on a global scale, if you include atmosphere, land, ocean, and then the coupling terms, we can very much get back most of the skills. So this is kind of nice because it shows that the problem is sort of linear, and it's less linear in other places. So in the tropics, the sum is a little bit greater than what the skill is. And there's some, and I think that's largely to do to the ocean-atmosphere interactions. Sometimes it's like counting the term twice. But in short, what you see is in the global mean, the atmosphere is the largest source of predictability in the early weeks, and the ocean really becomes important in the tropics, but in regions like mid-latitudes and high latitudes, it has a very small role. And at least in our model, the land is nowhere to be found except for these very few, very early stages of the forecast. And the reason we believe there is this green term comes up in the very beginning is that because anytime that you initialize the atmosphere correctly, then the land is going to respond very quickly, and vice versa. So if you initialize the land that was forced by the realistic atmospheric temperatures, then that interaction to the atmosphere transferred very quickly. But in short, the role of land in our model is very weak. And this is similar for precipitation. So in the tropics, you can see that most of the predictability is still coming from the atmosphere, but the role of the ocean is really increasing in weeks 4. Land is nowhere to be found, but in mid-latitudes and in high latitudes, really there is only skill in the weeks 2 to 4, and it's really primarily coming from the atmosphere. So those are a little surprising results. So if we go back to Paul's diagram, so his was made for mid-latitudes, 30 north to 60 north. So then Sasha remade this figure exactly as to be comparable, and this is what the two would look like. So clearly there's 2 possibilities here. Either this land atmosphere, the role of the land is really overestimated in this diagram on the left, or there is really something that needs to be worked on in CSM in order to capture those interactions with land, and those are the things we're going to explore with the land group, like the R-tuning parameters that can be changed in the model, and a lot of things change between CSM1 and CSM2, and we don't have these experiments for CSM1. So hopefully that's something we can work on in the future, is trying to figure out whether those tuning parameters can be changed and whether they would change how this diagram looks like. So that's it. Results suggest that the atmospheric initial state is the dominant source of 2-meter air temperature predictability through weeks 3, 4, and especially in the high latitudes and mid latitudes. and the land initial conditions really play a small role in our system. And the predictability from the ocean initial state is comparable to that in the atmosphere and the tropics only, and there is increased skill during active ENSO and especially in those tropical regions. So this work just got published yesterday, so you can see the paper online. And I'll give you a little bit of preview. We have now a student from Monash University. She's also looking at the MJO in these simulations. So color coding is maybe slightly different, but the results are kind of similar what you would expect. So the blue line is when we remove the atmospheric initial condition, and the skill of the MJO really drops to almost nothing. And not really surprisingly from the previous results, when you change the ocean to climatology, you have a reduction of skill, but it's not as detrimental. So she's going to look into that a little bit more. And I think Sanjeev's student Yanan has also been looking a little bit into soil moisture, and I think she's presented it before. I think the paper is coming out. And the simulations are all available online if you'd like to look at them and look at other aspects of the simulation.
We have about 2 minutes. If there's questions, either online or in the room.
I have a comment and a question. So first of all, I feel like the changes, a lot of what you were seeing in the land atmosphere coupling is related to there being more snow in CSM2, right? It was in the very high latitudes in the summertime and then over a broader area in the wintertime. And I feel like the coupling between soil moisture and latent heat flux is not really the relevant metric when there's more snow.
It's true, and I think we looked at the snow initialization, and it was also not as great as we would like to see in CSM2.
Okay. All right, I forgot these are initialized, so I guess I don't
Yeah.
know about snow and initialized predictions, but definitely CSM2 has more snow and more dense snow that kind of stays around for longer. And then my question was whether you've looked at other metrics that might care more about the magnitude of the anomalies. Like I could imagine the land might impact, if you're going to predict a heat wave, maybe the model's going to do that anyway, but maybe the magnitude is going to be predicted better with better land initialization.
I think Abby has ran through the whole suite of other metrics that she had, and I think more or less the outcomes were the same. Yeah. But yeah, I think the snow is another part that we should look into. Because yeah, the initialization, we had the land group look and show us all the diagnostics, and there were big differences from what it looks like in observations, but the observations are also not perfect, so. Yeah, that may be another piece of the puzzle.
We have time for one more.
Sure.
I was wondering if you looked at this in like a perfect predictability framework, also just looking at the prediction of one of the ensembles versus how it compared to observations, especially in something like CLIMO runs, and see if those figures sort of agree.
We have not.
Cool.
It's a really good idea.
Yeah, it's a great idea.
Kathy, do you know how to check if there are online questions?
And also let's go to Amy Rule's talk.
We're just trying to check there's online questions and how to see them, if there are.
So I'll just make one comment, and we can talk about it later, but I think you talk a lot about the land atmosphere coupling unexpected results. I was kind of shocked by the ocean unexpected results. I kind of expected the role of the ocean by the time you got further out there to have to play a role, and I don't know, I was a little surprised to realize that it didn't.
Yeah, I guess so, yeah, there have been a lot of, I guess that shock was a little smaller, and but yes, we learned that when we first ran one sweep by mistake, when our ocean was lagged by 1 year, so it was off by 1 year, and we didn't see any change in skill. So yeah, we didn't publish that experiment, but that was our first hint that the ocean doesn't, that's why we're asking whether, it doesn't matter, can we just put a real-time forecast with climatological ocean, basically, because we're not seeing it, doing a whole lot.
Paul?
All right, let's, yes,
Cancel.
so just click cancel.
And Eniola, are you available and ready to present?
Can you hit cancel? Thank you. Are you trying to bring up the next?
Well, yeah, I'm trying to get Eniola to present remotely.
Oh,
Is he lined up?
he's online. Eniola, are you online?
I saw him just a minute ago.
He must have dropped out.
Is he in a breakout?
Here's our agenda.
Can you switch back?
I can go, or you can have Tim Higgins go.
All right, well, maybe we'll have Kathy give her presentation and we'll see if Eniola comes back. Sorry we're not keeping to the agenda, but right here.
All right, well, this works out nicely because I'm using some of Yaga's experiments. So I'm looking at sources of subseasonal precipitation skill in South America, and I really do want to acknowledge this is a great set of experiments that Yaga, and I think Sasha was also involved, so I want to make sure in running these, so I make sure often the people who run the model don't get the credit they deserve, so I want to make sure that the people who did these runs get the credit they deserve for this. These are a fantastic set of runs. So this is showing you a figure from sub X. These are all of the models in sub X along with the skill of precipitation at week 3, 4, I can't remember which one I pulled. But the point is that if you did a global plot of the subseasonal prediction skill of precipitation, that global plot is mostly white, showing no significant skill. The only region that has skill on these timescales for precipitation is in Brazil. And so this is, the skill's not super high, but this is a skill over all months, all years, at individual grid points. So what this is telling us is there are times when there's higher skill in this region compared to any other region over this hindcast period. So where is this skill coming from? And interestingly enough, my assumption would be that there's, being in South America, maybe there's a close to Atlantic Niño and, Pacific Niño, maybe there's some ocean role going on here, bringing some skill. But really, I don't exactly know where that skill is coming from, and I wanted to know where our only source of subseasonal precipitation skill globally is coming from. So that's the question that I'll be trying to answer. I don't have a full answer yet. It's a workshop, so this is very preliminary results. So this is my table that I made of these subseasonal hindcasts that Yaga just described. And so it's this whole suite. We have the control.
It's on the main screen.
There we go. Okay, yeah, this is a little awkward, I'm not used to this. Anyway, so we have the control, which is your standard set of hindcasts where all components are initialized properly with initial conditions. And this entire suite that Yaga described, we're holding certain initial conditions to CLIMO and basically doing every combination of that allows us to diagnose sources of predictability based on initial conditions. So just to convince ourselves that we're working in the same kind of space, this is just showing you the skill of CESM precipitation in South America from the control hindcasts, again compared with the the sub-X models. And just to be clear, we're working with very similar skill here. It's not like CSM is terribly different from the other models. It has, skill in basically the same region. So then when we start to look at all of these different experiments and the skill associated with these different experiments, and the way I've labeled them is this is telling you what's being held to climatology. So in this case, the ocean, we were initialized with ocean, climatological ocean, everything else was a normal initial condition, real initial condition. And so what you can see is when you compare all of these to the control standard set of hindcasts, you come down here and you see really you can recover most of that skill when you hold the ocean and the land to climatology. So it's really the atmosphere that is the source of most of this. You do see a little bit when you hold the atmosphere and the land to climatology that there's some component here coming from the ocean, but the large majority of the skill in South America is coming from the atmosphere. So the next question I wanted to know is like, all right, well, there's probably some seasonal variability to this skill. So what seasons is this skill coming from? And can that sort of, by just, looking by different seasons and by the different components, can we get a sense of what's going on? And so I'm showing you here just the different seasons when they initialized by the ocean and the land as climatology and the atmosphere as real initial conditions, and compared with the control. And you can see, the highest skill is coming in DJF and SON, and then we're really finding that the majority of, you can recover most of the control skill, sorry, I'm in trouble with this pointer, most of the control skill in these two seasons from just the atmosphere initial conditions alone. We do see in March, April, May, we see some skill coming from elsewhere. And if we add the ocean initial condition with the atmosphere and the land as climatology, you can see that there is some component here coming from the ocean, a little in DJF and a little, that's where some of that additional skill in March, April, May is coming from. So like I said, these are preliminary results, short presentation, just to give you an example of, really I feel like it's an example of the kind of questions we can ask with this incredibly rich data set. And so really looking at trying to understand these sources of predictability based on initial conditions. And again, we're finding similar to what Yaga found, showing the temperature, is that the atmosphere is the primary source of predictability. Excuse me, on these timescales, we do see some, from a seasonal perspective, the ocean as a small secondary source of predictability. We see low skill in JJA, mostly from the atmosphere, what's there. And again, we're not finding the land initial conditions to be important. Again, this is a model-specific result, so as Yaga pointed out, this could be a function of the model itself, or it could be a function of predictability and the role of the land. I think we don't know the answer to that question at this particular moment in time. And certainly not from these experiments. I think this is the kind of thing that if we could get another modeling group or a collection of modeling groups to do these kinds of experiments, allow us to see more broadly across our models, I think it would help us to answer some of those questions about whether this is a model-specific result or more broadly a representative of the role of the land initial conditions. And so really this has only touched the surface of looking at what are the sources of predictability in South America precip. The next steps are to, I wanted to look at the atmosphere, try to figure out what atmosphere initial conditions are associated with skillful forecast. So separating out those forecasts that are skillful and then seeing what are those, what setup, what situation, and it may be multiple. We may have to do some sort of clustering or something. But this is along the same lines as the work Kirsten has done with machine learning models to take the confident and skillful forecast and then try to understand where is that skill coming from. The challenge here is, I'm not showing it, but I did some reliability diagrams, and the ensemble suite is not very reliable. It's highly overconfident. So using the probabilistic information from the model and trying to find a most confident and skillful forecast as our sort of metric for pulling out what is the model picking up on, I don't think is going to work too easily without some sort of calibration. That's not to say this is not meant to be a statement that there's something terribly wrong with CSM2. Most models are overconfident on these timescales. This is sort of a nature of our ensemble, how we design ensemble suites and our ability to properly represent that uncertainty. But most of our dynamical models tend to be overconfident on these timescales. But then the goal is, once we can identify what's going on in these cases where we have skillful forecasts, can we then pick out some potential predictors and maybe do some causal analysis to try to then connect how these predictors are leading to this additional skill. So that's the goal of the project. Again, very preliminary results, but I'm happy to take questions.
I'll just make a comment. I really like how you put it against the other sub-X models, because then I think it gives the weight of the study a little bit more detail, because the patterns of precip skill are the same as in all the other models. So clearly CSM is not doing anything wrong, right? If anything else, it looks like all the other models.
Either everyone is wrong.
Exactly, either everyone is wrong.
Which is entirely a possibility.
Yes.
But see, yeah, there's nothing uniquely wrong about CSM, right? The results coming from CSM seem to be consistent information with what we expect from these other models. But I do think we need to do those experiments with the other models.
Does the MJO affect precipitation in that area? Do you think that's what's causing it?
I don't tend to think of the MJO as a big factor in that area, mostly because by the time the MJO signal is sort of affecting that area, you've lost the convection part. It's really only a circulation component. And so, I mean, I guess it could be, having some circulation impact that we don't fully understand. But, I had really expected like an Atlantic Nino and a Pacific ENSO to be a big factor here, given the location. I wasn't expecting MJO to be a big component, but it's certainly something that should be investigated.
Yaga showed that in the climatological land initialization that improved temperature scale over this region that you're focused on. So I think you showed that, and I'm just curious if you got improved precipitation scale.
Yeah, so this would be climatological
It kind of
land.
looks like you do get improved.
Yeah, climatological land is, someday I'll make some
Over
sense.
northern South
Yeah.
America.
You do get some improvement, I think, but I don't know that I guess I wasn't convinced it was some big improvement that at the same level, I think, as what Yaga was seeing in the temperature. Again, the other challenge here is, we're working with small correlations, and so I tried to not focus on too many small areas that had slight differences in correlation, because I wasn't convinced that would be really, and I didn't do the actual difference calculations. So
Is this all seasons?
this one is all seasons, yes.
Because the land initial conditions, oh, sorry.
Well, I did, so I'm not actually showing you the one that's only land, that's where, in this one, because I was pulling out just showing you the ones where the difference was mattered by season. But I do have those by season for each of these, each set of experiments, so we could look in more detail, but.
Because the importance or the influence of the land initial conditions depends a lot on the season.
Yeah, but I didn't really see, I'm trying to remember off the top of my head, but there's very little, I think, impact when you look at the different seasons when you look at the different seasons, when you just look at only the land initialized, basically there's almost no skill when you only initialize the land, and so the difference between the seasons didn't vary too much.
And in our study, we didn't show it, we only showed annual means, but we reran all the seasons and there was no large difference, there was slight variation. But we didn't find the diagram looking any different if we did it by season. So that's the whole mystery, it's really not, all the processes that we think vary and they should matter, they're showing not to.
Yeah, we take that offline.
I had another question about the reliability. Have you looked at the shortest lead time, say 1 week, which would kind of reflect the reliability of the spread in the initial conditions? So that's one question. Is it an issue with how we're initializing and introducing spread in the atmosphere? Or do we just have too small of an ensemble? Do you think that-
Yeah, so I did look at the shorter lead. It's the way the ensemble is designed, initialized. It's not, and again, that was not meant to be a criticism of this is a widespread problem of properly representing the uncertainty in the initial conditions is a widespread problem broadly in our dynamical modeling systems, right? And how we do that properly and well and so probably I'm trying to think, I played around with some ensemble size. I suspect it's not the ensemble size, it's the way the ensemble is designed is not properly representing that uncertainty to start with.
That's really helpful.
That would be my best off the top of my head remembering the stuff I was playing, but I wouldn't proceed without further quantifying that with making changes, right? Are there any online questions? Questions here? I'm not seeing. I see a clapping hand from Sanjeev.
Can you try to get any on that?
Yeah, we've got him. We just need to download his talk.
Okay.
Kathy, while they're downloading the talk, can I ask?
Sure.
So with there's a whole new suite of these machine learning models that are super cheap to run, and probably because of that, much more easy to calibrate. So we can kind of go after those spread questions. Is there anyone starting to think about this space to look at the subseasonal forecast there and do you anticipate?
Yeah, so we I know that there's some people, Stefan Rask is at Google, and he's starting to extend some of their machine learning models out to subseasonal timescales. And I think they're also playing with some ensembles. But I think this whole how to do ensembles with machine learning models is still an open question. And most of these new models that have come out are NWP timescale, and very few people have tried running them to the subseasonal timescale. So I feel like we have this really big open question about what are they going to do at the subseasonal timescale. And I'm excited to see, I'm really excited to see what they can do, and I think we need to bring our community to that evaluation in order to do a really good job of understanding, because there's a lot of promise and excitement, but until we evaluate them at the same level of, just picking them apart like we've done with our dynamical models, I'm hesitant to feel confident in them, at least myself, and I think other people are as well.
Thanks.
Yep.
All right, so he's ready to go.
Okay.
We're
And
gonna
I'm
have to
gonna-
run his slides
okay.
for him.
All right, Eniola, you can go ahead. Let me just introduce you. This is Eniola Olanian, enhancing heavy rainfall forecasting in high resolution regional models over West Africa for operational application. So go ahead, Eniola, and I'll advance slides for you.
And you press enter. Good day, everyone. There is 5 key things that an operational forecaster wants to know. Please enter. He wants to know if it's going to rain. Enter. He wants to know how would the rain be. Enter. He wants to know when the rain will fall. Enter. He wants to know where the rain will fall. And lastly, enter. He wants to know how heavy the rain is going to be. And these are being the crucial question that eludes every forecaster on the bench. How heavy is it going to be? Please enter. That is the reason we are talking on this topic now, enhancing heavy rainfall forecasting in high resolution regional models over West Africa for operational needs with all these wonderful scientists. Please enter. Basic aim, please enter. This research is aimed to reduce environmental hazard of flooding on the last mile communities by improving how we forecast every rainfall from a high resolution general model, and with a specific objective of developing an improved every rainfall forecasting tool using machine learning techniques in Africa. Please enter. Previous study, enter. From our previous study, we found out that areas of heavy rainfall in West Africa are mostly 100 to 300 kilometers southwest of the core of the AEJ. They normally coincide with areas of increasing cape and areas of decreasing pressure. We also noticed that not every storm in the east of the prime meridian, which is around here, is associated with Africa easterly wave. Please go ahead. Next slide. We find out from the correlation of Cosmo with the Cape and mean sea level pressure and the structural comparison of the AEJ and the Africa easterly wave. We notice that the Cosmo model is able to reproduce the atmospheric dynamics modulating heavy rainfall. We show that this reproducibility of the forecast to produce synoptic pattern does not transform into predicting heavy rainfall. So we suggested that operational forecasters may be able to determine likely areas of heavy rainfall by estimating the position of these dynamics in Cosmo model. Next slide. So if our conclusion is that forecaster may determine likely areas of heavy rainfall by estimating the position of the EJ core based on the position of at the least falling pressure in Cosmo, the question will now be if it is possible to develop a method or a techniques that could detect similar pattern of synoptic feature as produced by Cosmo model in historical observed records. And can we use these identify similar pattern to predict areas of heavy rainfall? And if we are correct, or if this comes out to be effective, at what degree should we expect its accuracy? Please. To carry out this, we source our data from 3 sources. We use ERA 5 to source for the synoptic variables, and satellite GPMI match for the ground truth rainfall from 2001 and 2022. And the simulation is performed for 8 different high impact weather events from 2015 to 2022. Next slide. In the month of August. Our method followed 5 simple ways. 1 was simulate the Cosmo model for these high impact events. We compile and computed the historical data from 2001 to 2022. We apply this in the machine learning using k-mean clustering. Then we generate the enhanced rainfall forecast. Then we apply the evaluation metrics. Next slide, please. Cosmo simulation. Next slide, please. This is the Cosmo configuration that we use. The Cosmo is run on a regular grid of X about 529 and Y 305. And we have the forecast time of about 60 hours to run at time step of 3 hours. Next slide, please. Computing history. The computation of the binary values that were used for 4 synoptic variables that define the condition for heavy rainfall is carried out in this way. The Cape tendency that is equal to or surpassing 95th percentile indicates the areas of rising Cape. The 5th percentile indicate the area of falling pressure. We consider meridional wind between -5 and 0 meter per second for the Africa easterly wave. And that we use the zonal wind at 600 millibar level that is equal to or greater than 95th percentile to determine the core of the AEJ. Next slide. We now overlay each of these synoptic variables map with each other in this way to have 6 synoptic variants as you can see it, as it appears here. So these now serve as the input data for the machine learning, the clustering application. We have 690 for each of the various synoptic variants that we have each day. So next slide. Apply K-mean clustering. Next slide. So K-mean clustering is an unsupervised machine learning tool that requires no data label for training. What he used is pattern recognition that is its ability to discover pattern. It does this by grouping similar pixel or signal component images and process them into clustering. But to ensure the effectiveness of the clustering process, we employ the elbow method to identify the optimal number of clusters. Next slide. So when we do the clustering of the AEJ, AEW, and the mean sea level pressure, we could get this number depending on how effective the clustering is on each of the synoptic variants determined. Next slide. How do we generate this rainfall forecast? Next slide. So an algorithm search through the clustering that we have created. It identified the group that contained the Cosmo case study under consideration. Following the identification, the corresponding dates, that is, doesn't include the simulated dates from the rainfall data aligned with the identified group, are extracted. Then ensemble mean is computed, treating each raining day data as an ensemble member. Then we now compute the binary representation of the rainfall accumulated equal to or exceeding 90th percentile as the heavy rainfall. This refined pattern serves as the enhanced rainfall forecast for each of the synoptic clustering process. Lastly, we generated 2 probabilistic forecasts by combining all the derived synoptic clustering outcome and all the derived synoptic outcome with Cosmo. Next slide. So how do we evaluate this? Next slide. We use 2 evaluation metrics, the correlation and the fraction scale score. The correlation is to determine the linear association of the forecast with the observation. And we use the fraction scale score to indicate at what spatial area is the forecast reliable. And we apply it over the west of prime meridian, the east of prime meridian, and all over West Africa. Next slide. This is the eyeball comparison between the uppercase is the observation for each case study. The second uppercase is the observation, is the simulated rainfall from Cosmo model for each cases. And the last 2 lower panels are the probabilistic forecasts generated from all the synoptic clustering. And the last one is all the synoptic clustering and Cosmo model. And if we look clearly at this map, we will see that there is a clear evidence of the uniqueness of each of the synoptic interaction. And we could see it improving when we combine in the probabilistic forecast. Next slide. Oh, no. Okay, that's good. We computed the correlation, and we computed correlation for each of the synoptic pattern across all the cases. For instance, we could see that the interaction of each of these is unique in all the region. You can see, but they are when we look at the west of the prime meridian, we can see improvements in each of the clustering, and of course, there is also an improvement when we consider the probabilistic forecast for all the clustering and all the clustering with Cosmo model. Next slide. This is showing the fraction scale score for neighborhood size from 10 to 650 kilometers over the West Africa, the east of the prime meridian, here, and the west of the prime meridian. And the spatial scale at which each synoptic clustering are reliable, we can see differs for each of the synoptic clustering. And we could see also that the Africa easterly wave, as represented by this cyan color, also as it show of not having any good skill here, still show in case 4 of having the best skill there. Next slide. So this figure is showing the analysis of the correlation from all the correlation of all the synoptic clustering, and the FSS for 10 kilometer neighborhood size, which is the B, and the C is the neighborhood size at FSS equal to 0.5 for all the case studies. And we could see here that the west of prime meridian shows strongest correlation. It showed the strongest FSS at 10 kilometer resolution and the highest spatial resolution where FSS is 0.5. We could also see that, however, the clustering of the Africa East wave, Africa Easterly wave, showed the highest FSS in here. Next slide. This is showing the analysis of yearly fraction scale score for 10 kilometer neighborhood size from the clustering of the ensemble, the ensemble of all the synoptic and the ensemble of all the synoptic with Cosmo model. And we could clearly see that over West Africa here, in most years, the forecast from the clustering is better than that of the Cosmo model. Although in other parts, they are very close. Next slide. The preliminary results. Next slide. In all, we have seen that the results indicate, regardless of the specific weather event, each synoptic clustering procedure generates unique rainfall forecast attributes. We have also seen that the generated probabilistic forecast captured the observed spatial distribution of heavy rainfall over West Africa, particularly west of the prime meridian. We have seen that the fraction scale score from the ensemble of all synoptic cluster is stronger also over the west of prime meridian than the Cosmo and any individual synoptic cluster at neighborhood size of 10 kilometer resolution. We found out that both Cosmo and clustering system may display close skill throughout the case period, particularly west of the prime meridian. However, the clustering generally feel better skill in West Africa. Finally, I want to say that this study alights on the unique characteristic of synoptic clustering in enhancing rainfall forecast by employing unsupervised machine learning techniques. And next slide. I want to thank the DWD for providing the initial data and for partly funding me. Next slide. And I will thank you for listening.
Questions for Eniola? Questions in the room or online? question. So Eniola, I'm interested in the idea that, you're looking at synoptic scale, sort of small scale types of predictions, right? When you're trying to look at where is it gonna rain heavy, right? And then, you've done a lot of work to get at that small scale. Can you talk a little bit more, and then you've also talked about, African easterly jet, some larger scale components. Do you think that we could use any of the information from these larger scale components, say maybe from CESM predictions on like subseasonal timescales, to get at some of this, to try to make predictions of this heavy rainfall in West Africa on these subseasonal timescales?
I strongly believe that it is possible. One, instead of looking at every unnecessary uh, synoptic drivers, we have identified 4 basic drivers that, whether you like it or not, they must be present if you want to have heavy rainfall, whether on the subseasonal time scale or in a numerical scale. If we could use these pattern recognition techniques, it might work also for subseasonal to seasonal time scale. I'm very positive about that. However, it demands that we have adequate data for the clustering, because it shows that the more the data, the better the results from the K-mean clustering.
Right, and so when you say adequate data, how much do you think, so we have these hindcasts that go from 99 to 2020.
That is not going to be adequate, because what I found out is that you will need nothing less than 50 years, because I use 22 years of GPM IMatch, and I've also tested it with fields that span up to like 40 years or 35 years, and I have seen the difference of the clustering. I've seen the difference in the clustering results, because if you want to go back in time to see how many times you have this pattern occurred, the more backward the hindcast you have, the better for the clustering to classify, the more the number of ensemble that you will have.
All right, great, thank you, Eniola. Any other questions for Eniola? All right, oh, we have a question in the room. Go ahead.
Yeah, I think I heard you mention that there's a time step of 3 hours in the model, and I wondered what that represents, and does that represent the extreme rainfall events that you're trying to study?
Okay, when you simulate the Cosmo model, it returns results every 3 hours. To compute the daily rainfall per day, we use 24-hour rainfall accumulation. And that 24-hour rainfall accumulation is from the 6th of today to the 6th of next day to indicate the 24 hours of today. So that is how we identify every day. We do not use the 3 hours. We accumulate the 3 hours into 24-hour rainfall.
Okay, thank you. I think I understand now.
All right, thank you, Eniola. We need to move on to our next speaker.
Thank you so much.
Our next speaker is Tim Higgins. There we go. All right, this is Tim Higgins, subseasonal potential predictability of horizontal water vapor transport and precipitation extremes in the North Pacific.
All right, hello everyone. I'd first like to introduce myself. I'm currently in my 4th year of my PhD at the CU Boulder Department of Atmospheric and Oceanic Sciences. And as of Friday of last week, I am also an ASP graduate student visitor here at NCAR for the next 6 months. So I'm looking forward to getting to know some of you while I'm here. First, I'd like to give a special thanks to my co-authors, Anish, Will, David, and Andrew for helping guide me in this project. It is currently in the 2nd round of revisions in the AMS Journal of Weather and Forecasting. So the primary motivation behind this study was another study from Labors et al. 2016 that looked at differences in the potential predictability of IVT and precipitation at the medium range. And this study found that IVT had higher predictability in the medium range. So what I wanted to do is see if this same relationship holds in the subseasonal range, and if so, what is causing it to have those differences. So like Labors et al. 2016, we only looked at potential predictability. So we allowed a single ensemble member from an ensemble forecast. Here we use ECMWF reforecast from the ECMWF S2S database. And so a single ensemble member functions as our model observation, and then the remaining ensemble members function as our forecast. I used ROC scores as a skill metric with a target threshold of 90th percentile conditions, so the predictability of greater than 90th percentile IVT and greater than 90th percentile precipitation. And I used lead times of 3 weeks and 4 weeks, so 7-day windows of conditions. Here's a great figure here from Kumar et al. 2014 that shows an example of differences between potential predictability, which assumes the perfect model, and actual predictability. So you can always expect actual predictability to have less forecast skill than potential predictability. I also wanted to investigate the relationship between North Pacific jet EOFs. So these EOFs were calculated in Winters, Kaiser, and Bossart 2019 from fields of upper level wind speed. And the leading EOF was the extension and retraction of the North Pacific jet, while the second leading EOF was the poleward and equatorward shift of the jet. Another study, Winters 2021, found that the North Pacific jet extension regime had some actual forecast skill out to week 4. So I was specifically looking at the connection between the jet extension regime and greater than 90th percentile predictability. So here's what I found when I first calculated ROC scores for IVT and precipitation at week 3 and week 4. Week 3 is in the panels on the left here. How does this work?
Point it at the computer screen and hold down. Yep.
Okay. So on the left we have week 3, on the right we have week 4, and then IVT on top and precipitation on the bottom. So the shaded contours are the ROC scores that I calculated. The unshaded contours are climatology of the 90th percentile of the jet extension regime. The hatch marks are locations in which there was some forecast skill using a Mann-Whitney U-test, which was shown to be appropriate for this type of problem in Mason and Graham 2002. And this red box here is what I used to define the jet exit region in this study. So as you can see here, there is some forecast skill for both IVT and precipitation all the way out to week 4 in some locations, and there appear to be some differences. So taking a closer look at these differences, I subtracted the precipitation ROC scores from the IVT ROC scores. And so anywhere where you see pink, IVT had greater forecast skill, and anywhere where you see green, precipitation had greater forecast skill. I used a student t-test to assess significance on these differences at the 95% level. So anywhere with the dotted marks, we have some significance. And so the main takeaway here is that there's a lot more pink on the screen than green. And so we see a lot more locations in which IVT has higher forecast skill. So the reason I selected this region here, for the jet exit region, was because it is on the leading edge of this jet extension regime. It is a location in which IVT and precipitation both had some forecast skill out to week 4, and it is somewhat close to the US West Coast. And here, I demonstrate why it is important to forecast IVT in this region. So I looked at the relationship between, on the top 2 panels, Well, on the top two panels here, I looked at IVT anomalies during weeks of greater than 90th percentile precipitation over the US West Coast, so this red box here, in both our ECMWF model observations and in ERA 5. And on the bottom two panels, I looked at precipitation anomalies during greater than 90th percentile IVT in the jet exit region. So we can see here is when we do see greater than 90th percentile precipitation on the US West Coast, there is positive IVT anomalies near this jet exit region that I defined. And when there is greater than 90th percentile IVT in the jet exit region, we do see downstream positive precipitation anomalies that are actually on the US West Coast. You will notice that in the bottom two panels, those plots do look quite a bit different, and I found that this was mostly a function of resolution, ERA 5 having a 1/4 degree resolution versus the 1.5 degree resolution in ECMWF forecasts. I then wanted to generate some error bars on these differences between the rock scores of IVT and precipitation at week 3 and week 4. So I used bootstrapping to do this. I had 5,000 bootstraps and 1,000 samples. And so positive values indicate IVT having more forecast skill, and negative values indicate precipitation having more forecast skill. And I found that in about 80% of the cases, IVT had a higher rock score in this region, in both week 3 and week 4. So I was able to establish that in this jet exit region, IVT had higher rock scores than precipitation did. And so I wanted to dig in a little bit into why we are seeing that. And so I took 2 different approaches to calculating rock scores at each lead time. What you're seeing in these plots is the shaded regions represent 1 standard deviation from the mean, which is shown in the lines. And I used a diamond marker at the bottom of the plot to indicate lead times in which these differences were significant at the 95% level using a student t-test. So in the plot on the left, what you see is when I took rock scores at each individual grid point and then took the mean of those rock scores and then plotted them at each lead time. On the right, what I did was I took the mean of the conditions first inside the box and then calculated rock scores and looked at the difference. One of the main reasons that Labors et al. Found that there were differences, one of the main reasons for why there were differences in IVT and precipitation predictability in the Labors paper was that IVT is associated with more synoptic large-scale conditions, while precipitation is associated, the predictability of precipitation is associated with smaller scale conditions, which is why I did this. And when we do this, we find a pretty interesting result. This gap certainly closes when we add spatial smoothing, but we see more lead times when IVT has more has more significant forecast skill indicated by these diamonds in the subseasonal range compared to the medium range. I then wanted to look more specifically into the impact of these North Pacific jet regimes on whether there were good skillful forecasts versus unskillful forecasts. So what you see here is a EOF diagram that was also introduced in Winters, Kaiser, and Bossart 2019. So it's pretty intuitive. You can see the anything on the right side of the phase diagram is a jet extension. On the left is a jet retraction. And in the bottom triangle is an equatorward shift, while the top triangle is a poleward shift. And so I used red to indicate forecasts that were unskillful, green to indicate forecasts that were skillful, and the darker shades indicate longer lead times. And so just looking at precipitation and comparing the unskillful forecasts of greater than 90th percentile precipitation to the skillful forecast. During the unskillful forecast, there really wasn't a signal from the North Pacific jet. We model observe climatology from it when we have unskillful forecasts of precipitation. While when there were skillful forecasts of precipitation, there was a bit of a signal, there was a bit of a jet extension when that happened in both week 3 and week 4. And then looking at IVT, there's a little bit of a different relationship. First of all, there's a stronger relationship between the jet extension regime and greater than 90th percentile conditions of IVT. So whether the forecasts were skillful or not, there was still a connection between the North Pacific jet and IVT. But when there were skillful forecasts of IVT, we model observed a stronger jet extension compared to when there were unskillful forecasts. And I used a student t-test to assess the significance of that difference and found that that difference was significant. So then finally, I wanted to look at the ensemble spread and the Rossby wave source and how that played into these differences in predictability. So what we see here is on the top 2 panels, week 3 and week 4, standardized ensemble spread during skillful forecasts of IVT when greater than 90th percentile IVT was observed in the jet exit region. So we have standardized ensemble spread in the shaded contours and geopotential height anomalies in the unshaded contours. And this ensemble spread is for upper level geopotential height. So geopotential height at 300 millibars. And what we see here is anomalously low ensemble spread sort of in the tropics in the Western Pacific and also in the mid-latitudes in the Western Pacific, and then downstream anomalously high ensemble spread. And so I wanted to look at the forecasted Rossby wave source at week 3 and week 4 during these forecasts. And what I found was that there is anomalously high Rossby wave source sort of upstream of this jet exit region. And in the unshaded contours, I showed the stream function. So we can see that when we do have skillful forecasts of IVT in this region, we have anomalously low ensemble spread in the tropics. And then in sort of that same region of anomalously low ensemble spread, we have anomalously high Rossby wave source upstream of this IVT that ultimately increases the chances of these conditions occurring when we observe it. And with that, I am going to explain some conclusions that I took away from this work. So I found that there is some potential predictability of both greater than 90th percentile IVT and greater than 90th percentile precipitation weeks that exists out to week 4 in the jet exit region. I found that IVT generally has more forecast skill than precipitation does over the North Pacific at subseasonal lead times. I found that local variability cannot fully explain these differences in forecast skill. And I found that the strength of the North Pacific jet can have a significant impact on the predictability of both IVT and precipitation in the subseasonal range. And so I think I have some time for questions, if anyone is curious about anything.
So if you have higher skill in the IVT, I'm wondering if there's any scope for getting higher skill in precipitation by kind of using the observed relationship between IVT and precipitation. Is that something you thought about?
You mean higher skill for precipitation downstream on the coast?
Yeah.
Yeah, I've definitely thought about how maybe we could use IVT in this region as an indicator for whether we might have anomalously high precipitation in that subseasonal range. I guess I'm not really sure how I would really incorporate that into a model.
And I guess if there was just like a straightforward linear relationship between IVT and precipitation, that maybe the model's not capturing in the same way as the observations, you could just use that and plug in the model-based IVT and come up with a kind of hybrid prediction for precipitation. But maybe it's not that simple.
It might not be that simple, but it's a really interesting idea that maybe Will has a better insight into that.
Yeah, so there is especially on the West Coast, there's a super linear relationship between upslope IVT and precipitation, captures something like 80% of the variance. So I think creating a statistical model based on some of this work could potentially increase some of the forecast skill. But again, we're sort of in this perfect predictability realm, so translating that from into real model space is also potentially strange.
Yeah, it would be interesting to run these experiments on actual model skill as well.
Yeah.
Could you clarify the Rossby wave source? Were you pointing to that strong feature over Japan as the source?
Yeah, sort of near Japan and east of Japan as well, which kind of coincides with this area, looking at the ensemble spread that's kind of just east of Japan.
Yeah, along those lines, I was wondering if you could elaborate a little more. I didn't quite understand your ensemble spread. It was less than something and more. I didn't understand the positive and negative, like what it was relative to.
So it's relative to the climatology of the ensemble spread.
Okay.
So we have less ensemble spread than normal in the blue areas, and then more than normal in the red areas.
And normal is like would be a standard climatology, like seasonally varying is the idea. You're capturing the seasonal variability of that ensemble.
Exactly, yep.
All right, should we move on? Thanks, Tim. That was
Yep.
good.
Thank you.
Who's up next? J-Ron?
Yes. It's on the, you got a agenda on the podium.
J-Ron, are you online and ready to go?
Hi, yes. Should I try to share screen now?
I think so. How do I go full screen here? Okay, great.
Okay. Are you able to see the presentation?
That's good.
Okay, thank you. Hi everyone, my name is Jairo Perez and I'm a third year graduate student at the University of Maryland. And I'm going to talk about the work we've been doing with Dr. Maria Molina on how to use machine learning to learn about the sources of predictability of weather regimes over North America. So the main research question we have is where does predictability come from? Meaning what variables or Earth system components contribute the most to that predictability, and what processes are associated with those variables or Earth system components. And the initial hypothesis or set of expectations that we have is something like what was shown in past presentations, which is the atmosphere being more important at the beginning of the forecast, and then after the second week of forecast, the land taking the lead in terms of contributing information, and then after 1 month, the ocean contributing the most to that predictability. So the next question, or before that, like the idea is to check these or to analyze how machine learning, if machine learning is able to give us some insights into this same picture. So one of the questions is what to predict. We know that we cannot try and predict small scale features at the S2S scale, at least for now. So we focus on the large scale atmosphere or features. And for that, we use weather regimes, which are easier to follow and understand than small scale weather events, but they also affect the surface and the occurrence of temperature anomalies, precipitation anomalies, storm tracks, and so forth. So the way in which we compute these weather regimes is based on a recent paper by Lee et al. That allows us to compute the weather regimes for the whole year round instead of only for the cold months. So we use biweekly fields of 500 hectopascals geopotential height. We extract a region over North America and remove the annual cycle and the trends. So we're left with the anomalies. And then to those anomalies, we perform a dimensionality reduction, and we are left with only 12 principal components, which represent around 80% of the variance of the anomalies over that region. After that, we use k-mean clustering to extract 4 categories from this time series, and those 4 categories correspond to the 4 weather regimes I'll be referring to during the talk, which are Alaskan Ridge, Pacific Trough, Greenland High, and Central US High. For our purpose, we also added a 5th class or a fifth class, which is the no weather regime class, associated with cases or samples in which the geopotential height field was closer to the zero or to the climatology. So after we have these 5 classes we want to predict, the next question is how to predict them or where to start in terms of looking for those sources of predictability. And this work is largely based on previous work from Dr. Maria Molina and others that shows that large-scale OLR and sea surface temperature patterns over the tropical Pacific and North Pacific are important and can act as precursors for the weather regimes. And they specifically found that skillful representations of those patterns in CESM within weeks 1 and 2 contribute to skillful predictions of weather regimes over weeks 3 and 4. So, for example, they found that that strong anomalies in terms of sea surface height in the tropical Pacific were associated with more skillful prediction of the Pacific Trough weather regime, or strong anomalies or patterns in terms of OLR, both in the tropical Pacific and in the northern Pacific, are associated with better prediction of the Greenland High regime or the Alaskan Ridge regime. So trying to include these into the framework, we also added more sources of predictability to our framework. So we use as predictors variables from the atmosphere, including OLR. We also use land variables, including soil moisture and heat integrated at different depths and snow depth. And we also use 10 variables from the ocean, including sea surface height, ocean heat content on different depths, and some ice properties. Now, the idea with these is after removing the climatology, the trends, and also performing a dimensionality reduction, the idea is to train different models with each variable individually to assess the capacity of that variable of predicting the weather regimes, instead of building a model that includes all the variables. So we'll build a different model for each one of them. The next question is what algorithm to use for classification. And in here we use XGBoost, which allows us to have a scalable framework, which means being able to train the model several times for different input variables and for different outputs. And the idea is that we use 20 principal components from one variable as inputs, and we predict the 5 classes of weather regimes, which include the 4 weather regimes and the non-weather regime class. So starting with the results, here's a comparison of the model's performance in terms of the F1 score for each one of the lead times, which go from week 1 to week 8. So in this graph, we have the F1 score for the best model of each component, including the atmosphere, the ocean, and the land. So in purple, we have the atmosphere, in blue, we have the ocean, and in orange, we have the land. So what we see initially, if we try and do the comparison with the hypothesis we have, is that we also didn't found the peak in predictability we expected, at least initially, from coming from land, which will be the orange line. However, we see that the atmosphere is most important at the beginning of the forecast, and then the skill decreases with time, and the skill coming from the ocean is more or less constant throughout the lead times. With this framework, we're also allowed to see which variables stand out as the best predictors, or the best predictors individually, right? So we see that from the ocean heat content at 300 meters or 200 meters was important. From land, we see integrated solid moisture being repeatedly the best predictor, and in the atmosphere we have a more mixed picture in terms of which one is the best predictor, but we see that upper tropospheric winds, which U200, are useful in week 2, for example, and OLR is useful in weeks from 4 to 6. Now, the next question is, how does this picture change seasonally? So if we look at the same plot for each one of the seasons, so in here we have winter, spring, summer, and fall, we see that there are high differences in terms of both the general skill of the machine learning models and persistence, and also there's high differences in terms of which component stands out as the best predictor. So the first thing is that we see that persistence is better during winter compared to other seasons, and the ocean still being consistently the better predictor, especially in summer and fall. However, we see that there are peaks in predictability at some lead times coming from land, for example, during winter and spring. And during winter, the snow depth appeared as the best predictor from the land, and during spring the moisture appeared as the best predictor during land. We also see sea surface height being highlighted as one of the best predictors at some lead times during summer, and from the atmosphere we see the decrease in skill rapidly during fall, but we also see some peaks at some points during the forecast. So in this case, for example, or in spring too. If we go and see how the picture changes for each weather regime, we also see big differences or large differences. We see, for example, that the Pacific Trough and Greenland height regimes are easier to predict than the Alaskan Ridge regime, for example. We see that from both the machine learning models perspective and the persistence perspective, which is this red line. And if we go and see which variables are more important for each case, we see that, for example, the ocean showed high importance, especially for Pacific Trough regime or Greenland high regime, with ocean heat content being the most important variable. And then we see land having some high relative importance for Alaskan Ridge in the latest lead times, or Central US high in week 5. And from the atmosphere, we see that U200 appeared several times in week 2 as the best predictor at the S2S scale. Now, the last part or complementary part of the study is based on those models that we found had the best skill in some cases. We went to see how the inputs of those models, which are the principal components, affected the likelihood of occurrence of weather regimes in the future 8 weeks. And that's one of the advantages of using principal components as inputs, that we know the spatial patterns associated with each time series. So in this one example from ocean heat content, this is the spatial pattern associated with the principal component number 0, and we have the time series associated with that principal component. So in this picture, what we have is when that time series is shows different values, going from lower values or below the 20th percentile to values higher than the 20th percentile, we see how the likelihood of occurrence of each weather regime changes in week 3 of forecast. So in this specific case, what we see is that when the time series is below the 20th percentile, which is associated in this case with La Nina being present, the Greenland height likelihood is reduced significantly, and the Pacific trough likelihood is increased. If we go and see other principal components, we found signs of the North Pacific gyre, for example, affecting the likelihood of occurrence of Greenland height and Alaskan ridge at weeks 4 and 5. We also went ahead and looked at variables from the soil, or principal components from the soil, and we found some examples of significant changes in the distribution in late lead time. So for example, if we see this spatial pattern of increased soil moisture over East Asia, Alaska, and Europe, we see that that is associated with a higher probability of Greenland height occurring at weeks 7 and 8 of forecast. We also see some relevant patterns associated with large-scale circulation from the atmosphere. So in this case, if we look at upper tropospheric winds, when we have upper level divergence in the Western tropical Pacific, either related to ENSO or MJO, we also see an increase in the likelihood of occurrence of central US high in weeks 1 and 2. And if we look at stratospheric winds, which we initially included trying to observe the effect of factors like the QBO or sudden stratospheric warming, we see that changes in the intensity of some stratospheric jets also change the likelihood of occurrence of Pacific trough and central US high in this case, for example, from weeks 3 to 5. There are other examples in OLR, mainly associated with ENSO and MJO. But we're currently preparing all those sources of predictability that we found or that we observed based on that framework of machine learning plus analyzing the inputs. We're currently writing that in this paper that is under preparation. Finally, I want to thank my group, the Climate and Extreme Data Science group at UMD, and of course NCAR for the computational resources and for providing this space to share the work. And I'll leave you with a summary, and thank you so much.
Yeah, Kirsten.
Hi, Jayron. It's Kirsten. Great talk.
Hi, Kirsten.
I was just curious, you might have said this and I missed it, but when you're training your random forest, did you give it day of year information, or for the winter time and springtime, for the different season analysis, did you train individual models for those, or is it just all one model that you split up into seasons?
Yes, that's a good question. We didn't train different models for each season. We trained, it's just one model for each variable and for each lead time. However, we included one variable, which was the day of the year, but in a cyclic form. So there is information in each model that is associated with the seasonality. And we also, like, apart from that, we have like the 20 principal components, which are anomalies, and the climatology is removed from those. So I don't know if that answers the question.
Yeah, it does. Thank you.
Mhm.
So I had a question. You mentioned that you used the fifth cluster being the sort of climatology cluster, but you didn't really talk much about that. Can you tell us why it was important to include that fifth?
Yes. So what we found is that in several cases, like looking individually at the samples, there were samples that were included in some cluster, but we didn't really see a good match between the pattern in the sample with the weather regime, right? So we did that mainly with the purpose of increasing skill, but also because in the Lee et al. Paper they suggest or they also include this fifth class of no weather regime or climatology class, and we found that it helped with improved predictive skill, and we also have looked a little bit about in terms of what initial conditions are important for predicting that class specifically, which is the no weather regime class. And we found two main things. One is that it is way harder to predict than the other four classes. There is since it's less frequent also. And but it is interesting that we found some spatial patterns or principal components associated with higher predictability of that fifth class, but we haven't looked in too much detail into that.
Just checking online if there's any questions. And I'm not seeing any, so if you have a question online, go ahead and unmute yourself because I'm not seeing it on the screen.
I have a question. Hey, Tyron, great talk. I wanted to ask about, so here you say the Alaskan Ridge is the hardest to predict. You had a note on one of your slides about how there was some land predictability coming for the Alaskan Ridge, and I can't remember. Oh, yeah. Okay. So I was wondering what variables that was for the land, and also if you thought about what the mechanism could be for land predictability for the Alaskan Ridge specifically.
Yeah, so I guess this is the slide you mean, right? There is an increase in predictability after week 6, that in this case is specifically associated with integrated soil moisture down to 1 meter of land. And the interesting thing is that after that, the most important variable, or the variable highlighted as the best predictor from land, is not soil moisture, but soil temperature. However, the skill still decrease. This is how soil temperature integrated or soil or proportional to soil heat. So in this case, soil moisture showed to be like the best predictor, and before that, snow depth also showed like high skill. In the manuscript we're preparing, we try and analyze this, but also looking at those seasonal differences because it's easier to separate those cases. However, if we look specifically at the principal components, like the one I showed in here was related to changes in Greenland high and Central US high, and I want to check if I have here the map. Yeah, in this case, this is another principal component 3 from soil moisture, and we see that decreased soil moisture in some areas might be associated with an increase in the likelihood of Alaskan Ridge. So in this case, for example, if we have lower soil moisture in this area, the likelihood increases. However, we haven't checked a lot into the literature to see if there is past evidence of this, or what are the underlying mechanisms under that happening. So it's like there's work to do still on that area.
Thanks.
Thanks, Jay Ron.
Thanks to you.
Thank you, Jayron. We need to move on now to our next speaker.
Yes, thank you so much.
Our next speaker is Kirsten Mayer, talking about exploring the relative contribution of the MJO and INSO to mid-latitude subseasonal predictability.
You know,
I think so.
It was already.
oh, I'm sorry.
Yeah,
Sorry.
yeah, well, you just got rid of it. Come on.
Can people see it?
No.
Can we switch the pin? Or should I do that?
There we go.
Okay, cool. Awesome. Hi, my name's Kirsten. This is some work I've been working on with Will Chapman, who just walked out the door, probably because he doesn't want to hear me talk about it anymore. And then also Tony Manriquez, who is our SOAR student over the summer. Unfortunately for you guys, this is my first time giving this presentation, so I hope it goes well. But please give me feedback if none of it makes sense. Okay, so of course, as you all know, given most of our talks have been about it, the subseasonal timescale is very difficult. I'm defining it here as about 2 weeks to 2 months, and it's often difficult because neither the atmospheric initial conditions that we often use for weather forecasts or those slower varying boundary conditions provide sufficient enough information for us to make actionable forecasts on these lead times. But there's this concept of a forecast of opportunity where sometimes specific conditions in our Earth system that are known to provide improved scale on these timescales can be used to make better forecasts on subseasonal timescales. And one of these opportunities is known as the Mann-Julian oscillation, or the MJO, which is this eastward propagating dipole of convection that propagates from the Indian Ocean into the Central Pacific over about 20 to 90 days. And it can affect mid-latitude weather, which you see in these contours here, on subseasonal timescales. And you can see this P&A-like pattern forming over North America as the MJO propagates. ENSO is also an important source of predictability. ENSO is an anomalous sea surface temperature pattern in the tropical Pacific, and it oscillates between anomalously warm, which is referred to as an El Nino, or anomalously cold, a La Nina. And also, as you see in these contours, it can affect this P&A region, specifically the Alaskan low area, which is going to be the focus of our talk. But often ENSO is thought of as a main source of predictability on seasonal timescales. But it does act as the background state for which the MJO and the teleconnections from the MJO propagate. So it can also influence subseasonal timescales. However, there's work that's showing that there is a subseasonal evolution of ENSO teleconnections due to changes in the basic state over the boreal winter. And so this really made us question about the relative contribution of the MJO and ENSO for mid-latitude subseasonal predictability. And if you know me, I love neural networks, apparently. So in order to address this question, we use an interpretable neural network. That says ENSO network and MJO network, if you can tell. The interpretable neural network is adapted from Gordon et al. 2023. It's also referred to as a neural additive model. And what that means is that we have two separate artificial neural networks here that are linearly combined in that gray box to make a final prediction. So we can start to dissect the relative contributions of sources of predictability from our individual artificial neural networks. So, and then also our data is from the CESM2 pre-industrial control run. So just to break down this interpretable neural network a little bit more, our ENSO network is only given information about the state of ENSO. And we use the Oceanic Nino Index to do that. And we also give it some information about the previous 15 days, which isn't very important for ENSO, but it is for the MJO, and we wanted to give it an equal amount of information. And then we also provided the day of year information so we can understand whether there's an importance, whether it's earlier winter or late winter, in terms of the importance for subseasonal predictability. So then we also have our MJO network. We use the RMM index to find the MJO. And in this network, we only give it information about the state of the MJO. You could argue that there's information about ENSO within this, but we do try to remove it. And then we give it this 15 days of previous information so it can understand the evolution of the MJO over that time period, as well as the information about the day of year. And so in this step, we're taking the prediction of the North Pacific geopotential height anomaly averaged over this box here at 500 hectopascals, and we're trying to predict the sign of that anomaly using the ENSO index and the MJO index. And then we linearly combine these predictions to make our final prediction. And we are really curious about the changes between the source of predictability between ENSO and the MJO across lead time. So we train a neural network to individual neural networks for leads from 5 to 30 days. And then we also were interested in the impact of our averaging our predictand, or that Z500. Often when we talk about subseasonal timescales, we talk about weekly averages. So we also wanted to explore the impact of averaging that final prediction. So we explore averaging windows of 2 to 30 days. But as you see here, we're just giving it the raw ENSO and the RMM indices. It has no information about whether this is going to be an enhanced predictability, like is it an El Nino, is it a La Nina, for example. But instead of defining what we refer to as an El Nino or a La Nina or a strong MJO event, we allow the neural network to identify these periods of enhanced predictability for us. So in order to do that, we use something that's referred to as confidence. And on the far right here, I have two examples of one of a high neural network confidence prediction and one of a low confidence prediction. So at that last layer, our neural network is actually outputting two values that sum to 1. And when the value is close to 1, that suggests that our neural network has high confidence in that prediction. And if it's close to 0.5, because it's a binary prediction problem, that suggests the neural network isn't quite sure whether it's going to be a positive or negative anomaly, and it makes it suggests that it has low confidence in that given prediction. And previous work has showed that when accuracy increases with confidence, we can use confidence as kind of a metric to identify our time periods with enhanced predictability or improved accuracy. So we can explore our neural networks, our interpretable neural networks performance across confidence values, and that's on the left here. We have 100 years of pre-industrial that we evaluated this on, of testing data. And we can see that as confidence increases, our accuracy is increasing. The lines I've shown here are the most extreme Z500 averaging windows, so 2 days and 28 days. And then the shading here is across all the lead times. So you can see that there's actually not that much of a spread between the averaging window scale and with also the lead time within that. And the other averaging windows fall within these two. And so I'm just trying to simplify the plot for you. And then on the right side, we threw reanalysis data, ERA5, at our neural network just to see the performance, let's see if it's identifying some physical connections that are important in the real world. And we find that our network actually performs relatively well on our reanalysis data, and also our accuracy is increasing with confidence, suggesting that our neural network is in fact identifying relevant forecasts of opportunity for our real world. And as I mentioned, we give our neural network day of year information. So on the x-axis here is month, November through February, and that's the month of our input. And then on the y-axis is the frequency of either a correct prediction or a confident incorrect prediction. A confident incorrect prediction are those forecasts of opportunity. And what we find is that for correct predictions, it's pretty level across most of the months. But when we have these forecasts of opportunities, we see a greater increase in forecasts of opportunity during the later years of the later months of boreal winter. And this is consistent with that work that I showed earlier about ENSO from Chapman et al., but also there's been work that shows that the MJO also has this late winter dependence on its teleconnections, Wang et al. 2023. So far, our neural network seems to be identifying some physically relevant sources of predictability. So now I'm going to take a step back and go back to that question about what is the relative role of the MJO and ENSO in mid-latitude subseasonal predictability. So going back to that final linear combination step, I wanted to walk through on how we could, for example, get a positive prediction. So let's say our correct prediction is positive. There are a couple ways that we could get a correct prediction. Either the ENSO neural network corrects correctly predicts positive, but the MJO network incorrectly predicts negative. But because of the weighting on that linear layer, we end up predicting a positive. And then vice versa, the MJO correctly predicts positive, but the ENSO network predicts negative. And then lastly, ENSO and the MJO network correctly predict a positive prediction. And so now, knowing this, we can start dissecting the frequency that the ENSO network correctly makes a prediction versus the MJO network correctly making a prediction, while the ENSO network or the MJO network incorrectly make that prediction. And so that's what I have plotted here. The y-axis is the frequency that a specific network makes a correct and or confident prediction. So the left is just for correct prediction. The ENSO network is in teal and the MJO network is in purple. And what we find, and the x-axis is lead time. And then this is just for a weekly Z500 average, but we get very similar results across the other Z500 averaging windows. So what we find is that as we increase our lead time, the frequency that the MJO network is making correct predictions while the ENSO network is not decreases, and then the ENSO network, as lead time increases, becomes more important for making those predictions. And the MJO network seems to be more important for making correct predictions at these shorter lead times, into about 10 days, and then after about 2 weeks, the ENSO network seems to be making more frequently correct predictions. However, it gets quite interesting when we start looking at forecasts of opportunity, or what the neural network identifies as forecasts of opportunity. And what we find is that across almost all the leads, the ENSO network more frequently makes correct and confident predictions than the MJO network. We can split this even further, so we can take these confident and correct predictions and look at negative and positive predictions separately. And we find that the negative prediction looks very similar to our just general confident and correct predictions. But what was interesting is that for positive predictions, while the frequency of a correct prediction is much less, we do see that the MJO and ENSO networks about equally contribute to correct predictions on this time scale, across lead times. We can also do something that's called permutation importance, which is basically trying to separate the input from the output. And so to make that a little clearer, what we do is for the left plot here, is we take our MJO information and we randomly shuffle it. And then we make predictions, and the change in accuracy between our not shuffled MJO information and our shuffled information can tell you information about the relative contribution of the MJO information to the total accuracy of the network. So we do that for MJO and we do that for ENSO. And so this is including all Z500 averaging windows here, but you can see there's very little spread in MJO, and it's about 5% of accuracy across confidence that there's a change in accuracy when we shuffle the MJO information. But when we shuffle ENSO information, we see that it's about 10% all the way to even close to 40%, depending on what averaging window you're using in terms of importance for predictability, and especially on those higher confident predictions or those forecasts of opportunity. So these results suggest that ENSO is a pretty big driver in subseasonal predictability, at least in this framework. However, we do have times when the MJO is important, and so in order to explore these types of MJO events that ultimately lead to predictability, what we did is we took our confident and correct predictions, specifically during ENSO neutral conditions, and we applied cluster analysis, k-means clustering, for the positive and negative predictions separately. And this is just the RMM phase diagrams for the specific phases of the MJO. And there are basically two types, even though there's 3 clusters, there's basically 2 types of MJO events that we see here. One is anomalously strong, which then decays into a neutral condition, or a neutral MJO, suggesting that we don't have that deconstructive interference from the MJO propagating into the later phases and switching the sign of that Z500 anomaly. And then we also find persistent MJO events, and that's in the upper left-hand corner here is a really good example of a very persistent anomaly. So overall, we find that our forecasts of opportunity are mainly during late winter, and that ENSO is a greater source of state-dependent subseasonal predictability overall in terms of the setup. However, when ENSO is in neutral conditions, we have anomalously strong and persistent MJO events that provide the most mid-latitude subseasonal predictability. And then we find that, that's something I forgot to mention, is that positive predictions during ENSO neutral conditions are about 2.5 times more likely than negative predictions when ENSO is neutral, suggesting that the MJO provides specific predictability for positive predictions over negative predictions. And that's this last point here, is that MJO seems to be particularly useful when we're predicting positive anomalies. Some caveats that you might have already thought about is that we're predicting the sign of the anomaly, and maybe the magnitude of the anomaly could change these results. So if we were to frame this as a regression problem, we could get different results. These results are also for the pre-industrial control run, and while we saw that it performed quite well in reanalysis data, our climate is changing, and so we may expect to see changes in the sources of predictability relevant for subseasonal timescales in the future. And with that, I can take any questions.
Thank you for a very interesting talk. Can you clarify again how do you define MJO and ENSO, and what is your target again?
Yeah, so let me see if I can just. So the ENSO index is the Oceanic Nino Index. Are you familiar with that?
Yeah.
Okay, great. And then we use the RMM index from Wheeler and Hendon to define the MJO. And then we, depending on using our specific lead and averaging window, we make a prediction of the average sign in that grid box over the North Pacific at those lead times.
So you're targeting the pattern of the potential height, or just
the anomalous sign, not the pattern. We average over that box.
Okay.
Yeah.
I had a question, Kirsten. So on one of your plots, you had frequency, and I think you were showing confident and correct predictions as a function of lead time. Not this one, earlier.
Not this one?
And the y-axis
This
was, no, earlier.
Earlier?
Yeah.
I don't have anything earlier for you.
Oh,
Is it this one?
it's the plot where you're highlighting the late winter increase. This one.
Yeah.
So it's frequency on the y-axis. Can you explain that? Are you really only getting order 1% of events correct?
Yeah, so this is daily time. This is daily events. And let's see here. Frequency 1%. You know, I'm gonna have to think about that one for you. But these are correct and confident predictions. And we look at the 20% most confident predictions, so that reduces our sample size a lot. But I'll have to get back to you.
Okay, thanks. Gaga, and then
Just related to the plot, like I'm curious if you went out to Mars, right? The plot keeps going.
Yeah. Well, we stopped it at the end of February because our last prediction was the end of March. So this is for the input data. But yeah, it would be interesting to look at later timescales.
Thank you so much. That was really interesting, and I will need to listen to it one more time before I can make a good question. But my question is if this correct and confident, does it have really the same information content in when we do ensemble forecasting? We have the reliability and that gives us the uncertainty. So that could be the confidence, and then the correct could be something like the anomaly correlation. How closely related are those really? That's maybe number one, and number two is, this is really interesting, but did machine learning offer sources of predictability that a dynamical model wouldn't have, or a traditional forecasting skill sort of study? And this is a real question, not a rhetorical one.
Okay,
Yeah.
great. I'm probably going to forget that second question, but
Yeah,
I'll try to
fine.
answer
Yeah,
the
yeah.
first. Okay. So confidence, you can kind of think of it, you can make those reliability diagrams with confidence as well. We didn't do that here, so I actually don't know how reliable the neural network is. Correct in this case is just accuracy, but you could kind of think of it, it's just a skill metric. We just look at how frequently it correctly predicts a sign over the total number of predictions. Does that kind of answer your question?
No, thank you so much.
Okay. Second question?
It's okay. Yeah, I mean, I guess I was trying to see what that network gives you that's new compared to the traditional thinking.
Yeah, so I guess in this case, what we are really curious about is the relative contribution of the ENSO and MJO.
Okay.
So we know that ENSO and the MJO are important based on our dynamical understanding. Yeah, so this was really, the neural network was mainly to try to use a nonlinear approach to explore the contributions from the MJO and ENSO. Yeah.
All right, let's thank Kirsten. We need to move forward. We can all have a short break before the CGD seminar starts. Sorry, it's my nap.